Hello everyone and welcome to the Advanced Data Modeling workshop. Today we speak about how to create an efficient data models for massively scalable applications. That's Aleksandr VOLOCHNEV, developer advocate at DataStax, and today with me a very special guest, Artem Chebotko, and we are very glad to welcome all of you at our DataStax developers channel. If you can see us, if you can hear us, please set your thumbs up to the YouTube chat and we will be very happy to start. Hi Artem.
Hi Alex, how are you?
Yeah, well, I'm doing great. I like Wednesdays because we always have some great content, but weather outside is like anyway asks me to stay at home, so it's a good time to run a workshop. And how it goes at your place?
Well, it's hot still in Houston.
I mean, how hot is hot?
Well, it's close to 80 degrees.
Oh my god, I mean, I'm not so good in Fahrenheit, but I guess it even sounds bad to me. That should be like around 30 Celsius or something like that, I think.
Yeah, maybe something like that.
Yeah, I guess so. Okay, so I see so many thumbs up and I see so many people are watching us live. So we will not waste your time anymore and we will immediately start. So, this release today is a little bit special to us because we have very rare guest in our area, Artem, and that's kind of legendary person in the field of Apache Cassandra and especially data modeling. That's basically the creator of data modeling methodology for Apache Cassandra. So today you will learn from that's even higher than from the best of the best. And person with altogether with dozens of publications and dozens of years in the database research and development. Artem, would you say a couple of words about yourself?
Well, I like data modeling. I work on different things, different data models for data stacks with our customers. I do a lot of educational content as well, and we will see some of that today. And thank you, Alex. And everyone already knows Alex. He's Apache Cassandra expert. He's doing a lot of workshops, so you are probably familiar. He's a great developer, and he's certified cloud architect as well.
Yeah, thank you, Artem. So, but today we work on your content, and so what was the things you was working last weeks? What we are going to show today?
Yeah, so I completed a set of data modeling examples from different domains, and we'll have a chance to take a look at maybe 3 of them today.
Yeah, so we did a lot of data modeling workshops before, but they always they had some lack of like real practical examples. So we were speaking more about the theory and not so much examples. But learning by doing and learning by example, it's like much more advanced and better way to learn things. So let's take a look on what we are going to do today. Before that, we are going to use multiple tools today. So the main tool for us is this video workshop. So we are going live on YouTube, and I guess we are going live on Twitch as well. Then, for the questions, you always can ask questions in YouTube chat. But as soon as stream is over, chat will be closed, of course, by YouTube. So some of your questions may be not answered by the time. We always suggest to use our Discord server. You can access that with bit.ly/Cassandra-workshop. And that's one of the best places to have like live conversations about some of the things you would like to discuss and maybe ask questions. Of course, we also have a community.datastax.com also to mention to ask questions. We ask some questions to you, and we want to play a little game and run a quiz. So those who will answer correctly and choose the proper answers will get some prizes. And I believe you attended some of our workshops before. And for practical steps of this workshop, first of all, we invite you to see how Artyom doing those exercises. That's always very cool to see how the highest level professionals are working on these kind of tasks. And also, we ask you, that's very important, not only watch. When you watch, you just that's half of your brain is working, maybe even smaller. But you have to push your own arms on your hands on the keyboard and type the commands. Only then you do learn the things for real, deeper. So we have all our exercises available absolutely for free at katakoda.com/datastacks. I will send you a link, and I guess some of my friends will send this link as well. We have, of course, not only 2 speakers, but as usual, we have much more people in the team chat, in the YouTube chat, and Discord answering questions. And before we proceed, we want to ask you some questions, because we would like to understand you better, and so we will know how much you have experience maybe with Apache Cassandra already, and some other questions we would like to have answers as well. If you attended one of our workshops before, you know what to do. Easiest way is to simply get your mobile phone, go to menti.com and use the code 566400. I repeat, 566400 to join our questionnaire and quiz later. In the quiz, you will need to be quick to answer not only correctly but also on time. But don't worry, that's just a warm-up to connect to Menti and answer very simple questions, so we will understand you. By the way, Artyom, what you would like to know about our audience today? What you would ask people about?
Well, anyone who has an experience with Cassandra probably had to do some schema design. If not data modeling, then schema design for sure, create tables, and so on. So just the number of years you used Cassandra would be a good indicator of your level in terms of data modeling and schema design.
Yeah, great. Yeah, we have this question in this questionnaire, and I see more and more people are joining. Once again, you have the link and you have the code right now on your screen, or maybe you can just scan the QR code as you are seeing at the screen, or go to menti.com 566400. So, let us start. And the first question is indeed very obvious. How much Cassandra or DataStax Enterprise experience do you have? And we have a very good distribution. So yes, that's interesting. We have people with many years of experience, and we have people who just started to work with Cassandra, and we have most of the people with basic understanding, and we have some people with no prior experience with Cassandra. So if you work with Cassandra for some time already, or you have at least basic understanding of how this great database works, then that's amazing. If you have no prior experience with Cassandra, this workshop still will be useful to you, but I strongly recommend you to watch one of our Introduction to Cassandra workshops. I always say what SQL is a bless and the curse of Cassandra. And people ask me, how come? Like, why? Okay, I understand bless. It's easy to learn. It's kind of pretty simple language, Cassandra query language. So what's the problem? Problem is, it looks very close to SQL. And then people who have experience with SQL for many years sometimes, they're like, oh, it looks exactly the same. I can use Cassandra, I'm ready. And well, no, you are not if you don't have explicit Cassandra experience, because it's different database. And SQL may look close to SQL, but it's not the same, and all the principles are different. So, please, if you have no prior experience, you need to attend Introduction to Cassandra. It's really worth your time to see how this great distributed system works and how one of the biggest companies in the world handle petabytes and dozens of petabytes of data with ease. Okay, so, but we have more questions. How much do you have, how much experience do you have with other NoSQL solutions? Not only Cassandra, but in general NoSQL world. How close it to you? There are a lot of very different solutions with different approaches. Okay, so again we have a very interesting picture here. And we have people who use NoSQL all the time, a lot, and we have people with no prior experience. So to say so, Cassandra is, from my point of view, one of the best solutions in the NoSQL world, but not the one and only. So in general, there are different solutions with different approaches, and those better pass to different use cases. Good. And finally, this one is a question from my side. What about normalization and denormalization? Okay. So most of the people have basic understanding or full understanding of what's the normalization and denormalization is. That's good. If you don't know those, again, we have a great, absolutely free Introduction to Cassandra workshop, where we usually speak also about the normalization and denormalization as well. So it may be a good idea for you to watch Introduction to Cassandra directly afterwards. And I think we are good to go. So that will be enough, thank you, and we are going to move on. And of course, I know you came here not because of me, but because of Artyom. So we will pass through this microphone to my colleague, and give me a moment to switch the screens. Yep, you could push the button. Yeah, so I will start this one. Looks great.
Okay, I'm actually impressed how many people know about normalization and can use it. But that knowledge is actually not required to be a good data modeler for Cassandra. And maybe I will explain why later. But we'll start with just some prerequisites, some basics, just a quick overview where you will either see that you already know that, or you will see that you need to actually learn a little bit more about basics of how Cassandra stores data. So at the top level, we have the key space, which is like a top container that will contain tables, indexes, your data, and so on. The importance of key space also is in the replication strategy. Here we have an example of creating key space with name library and specifying replication strategy and network topology. Strategy with two data centers, DC West, DC East, and replication factors 3 and 5. So anything that, any data that we will create here in this key space will have to be copied 3 times into one data center and 5 times in the other data center. So we'll have 8 replicas total storing our data. Then inside of key space, we create tables. In this example, we creating a table venues by year. And as Alex already mentioned, this looks a lot like just a structured query language statement. Even so, it's a Cassandra query language statement. The one difference, so you see the column and column names, data types. The one difference you see is a primary key. Somehow we have an extra parenthesis here, which actually define one subcomponent of the primary key. The primary key in this example consists of 2 other keys that we will talk about soon. Now, this first component, the first key, year, is actually called partition key. What it is for. The partition key defines how data will be distributed in Cassandra. So it divides your data into partitions. So there can be multiple rows that you insert into tables, into a table with the same partition key, which means there will be those rows will be grouped together, organized into one partition, and that partition will reside somewhere in your cluster on a replica node, and it will be replicated into multiple nodes. So in this example here, we have two colors, the green partition where year is 2019 and the blue partition where year is 2015. Okay, and we have multiple rows in those partitions. Okay, now with the definition of our data centers here, and the replication strategy for the key space, those partitions will be replicated among nodes in those data centers. So like we said, the replication factor for the COS is 3, so we will have 3 copies of that partition. And we'll have 5 copies in the other data center. Now, so the partition key is how data is going to be distributed. It's a unit of distribution. What it also means is that when you retrieve your data, you also ideally want to only access one partition to answer your query. Okay, so here is the second partition. It's going to have 8 copies as well. So now, in Cassandra query language, we have data definition statements, we have data manipulation statements. We are gonna, so you saw the create key space. We will talk about create table a little bit more. There are also indexes and materialized views. We're not going to use them today. They have some limitations in terms of use cases. So it's all the examples we're going to show, they actually don't require to use them, and most of the time it's beneficial not to use them because we can just create ordinary tables instead of secondary indexes or materialized views. Okay, and in terms of data manipulation, of course there is insert, update, and delete, but we will also talk select and about the rules for using select statement in CQL. So here is a create table statement. It has columns, each column has data type. Optionally, a column can be designated as static column. What does it mean? It does mean that its value cannot be changed. It means that all the rows in the same partition will share static column value. Okay, so essentially when you declare a column a static column, you will basically you're saying that this column describes the whole partition, all rows in the partition. So it's a partition level descriptor, and it's optimization to use it. When you use it, you save in space, and we will see some examples later. Now, besides the columns, we have the primary key clause here with 2 components. The first one in parentheses, the columns that constitute so-called partition key, and the rest of the columns will constitute a clustering key. Okay, so, and we will talk about clustering key shortly as well, what it is for. And the last clause here, the with clustering order by, defines the ordering for the clustering key columns. Okay, so based on this definition of the table, there are 2 types we can kind of classify tables into 2 types. The tables with single row partitions and tables with multi-row partitions. So let's look at this example. We have table users where primary key is simply user ID. So this primary key doesn't have clustering key, only partition key. Okay. So visually we have this kind of representation. K means it's a partition key. Okay, and what it means is each row, each partition in this table identified by ID will only contain 1 row. So this will be very similar to a relational database. That looks just like a relational database table. But in Cassandra, the most of the power comes from multi-row partitions, where you can organize multiple rows into a single partition, and you can retrieve that partition efficiently. And you can basically relate some entities and put them into one partition, and you can answer complex queries using that. So in this example, table artifacts by venue, we have venue and year, the composite partition key, so 2 columns. And they will be, so any row with the same venue and year will be part of the same partition. And then we have a clustering key column artifact, which will serve 2 purposes. First, it will uniquely identify a row within a partition. So each row within one partition will have a different clustering key value. But the second purpose of clustering key is to define ordering of rows within that partition. Okay, so by default, that ordering is gonna be ascending, but you can also change it to descending as if you need that. Okay, so here the visual presentation, we have the clustering key denoted here as C, and we also have the arrow that's showing that it's an ascending order. Okay, so now you can see at this visual representation, we have 2 partitions defined by venue and year, and we have multiple rows in each partition. So they have different artifact IDs, they have different titles, but they do share the same country because it's a static column. So the country is a static column. It describes the whole partition, all rows in the partition. Now, with respect to select close, now we can retrieve the data from the tables that we create, and it again looks very similar to SQL, but there are certain restrictions. So one important restriction, that if you never used SQL before, then you will notice that there are no joins. You can only specify one table in the from clause. So each query will only retrieve data from one table. And then in the where clause, you have primary key conditions and possibly index conditions. So you cannot query based on any column. It has to be a primary key column or potentially an index column. And there are additional rules how you can basically specify those primary key conditions. You will always have to specify partition key, complete partition key. If there are multiple columns, you have to specify equality there. And for clustering columns, you can potentially specify only some of them. And the last one that you will use can also be a range type of predicate, so it can be greater than or less than, and so on. It's possible to group by based on primary key columns, and ordering is defined only based on clustering key columns, and it's again within a partition, within each partition that you retrieve. But ideally, each query that you create, and you need to think about it in advance when you create in your data model, each query you create will retrieve only one partition. It's not always possible. There will be cases where you will retrieve several, a few, but your goal should be just to try to retrieve one. Limit should be obvious, number of rows you want to see, and allow filtering is something that tells Cassandra that you can scan data. You can scan data in your table, which is not efficient, so you should never use that. Okay, so here are some examples of valid queries here that we can express based on this table structure. We have venue, year, partition key, artifact, clustering column. Okay, so we can retrieve from this table where venue and year equals something, or where venue and year equals something and artifact equals something. And the last example, we can also have artifact that is greater than something and artifact that is less than something. So for clustering column, we can use range search, and we can enforce ordering. In this case, we change it to descending order for the clustering column only. So here are some examples of invalid queries. We cannot just query based on venue. We will get an error. We cannot query based on venue and artifact only, skipping year, because year, if you have a partition key, you have to specify all the columns. We cannot just query based on clustering columns alone. Okay, and we cannot query here in this example based on venue, year, which is partition key, but then title. Unless we create an index on the title, we cannot just query based on regular column. And finally, similarly, country, which is static column, we cannot execute query like that.
I would like to add a word on this slide. Could you please? Yeah, thank you. So from the very practical point of view, if you are the one who is responsible for continuous integration and like all the test related things like that, and your application works with Cassandra, you very probably may want to include one simple check to your code style checks, which is simply search for your code. Search in your code for allow filtering statement, because just one junior developer adding this statement in your application may heavily decrease cluster performance due to some really weird queries you don't want really to be executed on your production. So yes, as Artyom mentioned before, allow filtering is a big red danger label, and you don't want to have allow filtering in your production.
Right, and we can emphasize it again and again because it is important, definitely. Some other observations here. All right, so based on those table definitions, the multi-row partition, single-row partitions, and based on the queries, right, primary key purpose is to define a row or define uniqueness of a row in a table. Partition key defines data distribution and also uniqueness of partitions. It also can affect partition sizes, right? The partition sizes is how many rows you're gonna have in a single partition, because there are also kind of for efficiency, there are certain restrictions that you should follow. You should probably not create more than 100,000 rows per partition, or you don't want to have partitions that will have over 100 megabytes of data. But again, these are like soft limits, and depending on application, you may create actually for time series, you may with storing just simple values, you may still have larger number of rows in a partition and things like that. So, but it's kind of a golden rule of 100,000 rows, 100 megabytes per partition. Now, clustering key, it defines ordering within a partition, not within a table, but within a partition. And it also has to be, sometimes you just add in something into clustering key just to make sure that the row is unique within that partition. So it also serves uniqueness, that's why it's called key. Okay, and then in terms of query, when you define your queries, when you define your data model, you know that, well, the primary key is what you're gonna retrieve your data on. That's the partition key only allows equality predicates, and you always want to be able to only query or retrieve one partition or a couple of partitions. Okay, if you need ordering in your results, then you need to consider clustering key and how you're gonna organize it to make sure that you get that ordering. Similarly, if you need the range query, that's again clustering key. Okay, and only one table per query, no joins, which means you can store in the same partition, you can store multiple rows, and you can basically nest data in that partition that represents the result of a join. And we will see examples, many of those, because the Cassandra is all about multi-row partitions. Okay, so in terms of data modeling, so we had this overview. In terms of data modeling is more than just creating tables, right? Before you even start creating tables, you hear, okay, you need to denormalize data, right? But the question, what data, right? You also hear, well, you need to define your tables based on queries. But then again, the question, what data you're going to use, how that data looks like. So first thing, you will have to understand data. You will have to understand data requirements, define the entities there, relationships, constraints, what will be the keys, what will be the cardinalities. And then you focus on the queries, and then you organize and structure data based on queries. And then you only then you create your schema. You create tables and possibly indexes, and possibly you will need additional optimizations. Some of them we will discuss as well. But the data model is extremely important because it's going to make sure the data is complete, consistent, and accurate. You don't want to have absurds, for example. The data is queryable. You should be able to define a query based on that table, right? We said you cannot combine data from multiple tables. You cannot do a join. So you need to, and you cannot query on any column in the table. You need to design the table so that your query is supported, but also efficiency and scalability. So there are many things you look at when you're designing data models. And all of those things, you can think about them just in your head and hope that you will be able to design that correctly. Or you can kind of model it using steps, a framework, and using specific artifacts. To understand the data, traditionally, there is a conceptual data model that it's independent of database. So you can use it, and you can use it for any database. Okay, and then to identify access patterns, you need to look at the application that you are designing. Your application is not like, it doesn't have random access patterns, right? Those are connected. There are different microservices, if you wish, or tasks in your application, and they access data differently, but they also kind of run in certain sequences, and the result of one query can be used to execute the second query, and so on and so on. Now that will allow, so you understand now the patterns, how data is accessed. That will allow you to define the logical data model, which is now Cassandra data model, and it's based on queries indeed. Okay, and finally, there are certain optimization techniques that we will discuss, like splitting large partitions, that will define the final physical data model. So essentially, this is how the data modeling framework looks like. And we have the two additional things here, two processes, the mapping and optimizing. And those are actually the various data models. You will see we will visualize them. Once you've done the notation, they are not that difficult. They're actually very convenient to look at your data model and get the overall idea quickly. Okay, but the difficulty there is how we transition from one to another one. And we will see some examples today, but that's not the main focus. We're not going to jump into the most complex part today. Okay, and with that said, Alex is going to start with the first example.
Yep.
IoT data.
Yes, so give me a moment to switch. And we are going to have IoT data. So, first of all, thank you. That's very, very well explained things. It may be a bit too hard for those who don't have Cassandra experience, but well, we do beginner introduction to Cassandra workshops all the time, and now we want to give also something for those who already have practical experience. So stay strong, you can do it. After all, and we go to first practical example. So the row theory is great, but not so much useful as long as you don't start to use that and don't start to work with real examples and real code. And we have all of that for you today, theory and example and hands-on. And we start with the simplest possible example, which is a very good place to start, is a sensor network, or one of the kinds of IoT, Internet of Things networks. And exactly in this example, we are going to work with a global temperature monitoring sensor network. What's that about? So imagine we're speaking about meteorology or any kind of research where you need to understand not only the current temperature in the world, but also the dynamics and how it was changing over time, over years. So you can get some scientific data and maybe make some predictions and so on and so forth. Everyone wants to know which temperature will be tomorrow. Maybe it's not so in high demand as in year 2020. We most of the time stay at home, but hopefully it will be better next year. So what's the story with global sensor networks? There are a lot of sensors registering some values, in our case, in our example, temperature, and they're sending these data to a center, to a database, so you can process that later via internet. And those reports are usually pretty small, as they are just like register temperature. There are some bytes, timestamp, there are some bytes, and that's it. So they aren't big. But first of all, we own, in our example, really a lot of those sensors. And second, they send their state pretty often. So it depends, of course, on your story. We will cover a situation we want to track temperature, for example, once per hour. Although in many cases, sensor network, IoT network may send results once per second. But with our model, it will be fine as well. So, and exactly as Artem just said, we are going to cover a conceptual data model, application workflow, logical data model, physical data model, and final schema and query design. Let's move on. So, first we start with a conceptual data model. So we have to cover what are the entities we are working with. What properties do they have? And so what are the relations between them? Cassandra is a NoSQL and no relational database, but working with data, you need to understand its relations. And first we speak of the network. So network means what sensors are grouped into networks. For example, on the per country size, or maybe per city size, but something what groups them. Every network has one region where it's assigned to, has some number of sensors, has a name and the description. And obviously that's for people to be able to understand what is it and where it's located. When every network has many sensors, but one sensor may belong to only one network, so that's one-to-many relation. Working with sensors, every sensor has following properties we have to cover. That's ID, kind of very long string or integer. Then every sensor has a location, and to simplify, every location has latitude and longitude, so that's not an address but geographical coordinates. And of course, every sensor may have many characteristics. Those we will consider as just a map of key values. Then every sensor records some value, so it's a temperature network. It means we work with temperature. And every record has basically two properties: timestamp, when it was done, at which particular time, and the value, what was the temperature when it was registered. And the thing you see on the right is the entity relationship diagram. And I bet you've seen that before, at least most of you, because that's exactly the thing you use into the working with another databases. So that should look pretty clear for you. And means altogether we have three kind of entities we want to cover. Network has many sensors, sensor has many records, and one record may belong to one and only one sensor, of course. So it should be clear, this example is pretty simple. So Artem, maybe you would like to add something about conceptual data model here?
I don't know if you have questions, but the notation here. So this is a chance notation created by Peter Chen, and the notation here, the rectangles, they are called entity types, so like types of entities or objects, right? And then you have this double line temperature. What does it mean? So it simply means weak entity type, and what it means is that it doesn't have enough attributes to define a key. So its key is actually, you can see the timestamp is underlined using dotted line. So timestamp is part of the key, part of the temperature measurement identifier, but you also need to have ID of the sensor to uniquely identify that measurement. Okay. Mm. And so other notations you may see like double line for the characteristics, that means set valued attributes. So you can have multiple, and in Cassandra that will translate usually to map or maybe set or maybe some kind of collection. And then for the location, you see that there is latitude and longitude. That means it's a composite, the attribute, so it actually consists of multiple things. Like name may consist of first name, last name. If you need that distinction in your data model, conceptual data model, again, this is just you trying to understand data. You're not trying to model it for Cassandra yet. Okay.
Yeah, exactly. So that's the conceptual data model. That's not what we are putting to Cassandra. Wait a second and we will do it step by step. Okay. So we can move on and we go to application workflow. Application workflow is the definition of how exactly your application is going to work and what kind of the access patterns people are going to use to access the data your application works with. We can think of the application workflow, or we can also think, like I prefer to tell it, like the customer workflow or user workflow. So at some point we should think not only about the cold metal and applications and software, but also think a little bit about our customers, users, guests, you name them. So do things convenient for them to use as well. That's important. People first, after all. So application workflow or user workflow are the queries and actions we are going to execute to access the data. So we don't just store data, that would be weird, but we want to make it accessible for people to bring some value into the system we are developing or to the community we are working with and so on. So application workflow is designed with the goal of understanding data access patterns. That's the representation of application tasks and dependencies between them and data access patterns we are going to use. Ideally, each data access pattern you see on the right should specify what attributes to search for, search on, order by, and do aggregation on. And we, at this page, at this stage, we cover 4 main workflows we are going to cover. And the first one, the entry point for this application workflow is to show all networks. So we may have millions and millions and millions of sensors over the world, so it makes no sense to just show all of them at once. First, what you want to see is the list of networks to be able to pick one you are going to work with. And we are showing those sensor networks. That's going to be Q1, query 1. Find information about all networks, order by name. Order by name to keep it convenient for the customer, for user to try to find one of them. Then there are 2 possible following actions. In the Q2, we cover the use case when we display a heat map for the network. So we have a network, every sensor belongs to one network, and we can open the map, let's say, and see all the temperature state all over this network at once. And that's pretty understandable use case which have to cover. And that sounds for us like Q2. Find hourly average temperatures for every sensor in a specified network for a given date range. Order by date and hour. Notice there are some interesting things. We will need some average temperatures for every sensor in the network for a given date range, and they has to be ordered by date. So, and we are going to work not with the last hour, let's say, but also date range may be changed. So we may need to have like show latest first, but that must be configurable after all. In another case, we speak about Q3, display all sensors in a network. That's again pretty obvious step. When I open a network, I may want to see what are the definitions and what values they have and what's their current state and so on and so forth. So that's important to be able to find information about all sensors in the specified network. And finally, as a consequence of Q3, we have a Q4. Find raw measurements for a particular sensor on a specified date, ordered by timestamp. That's mostly, that's one of the easiest samples. You just have the list of the sensors. You push the button to open the details of one of the sensors, and you get the raw temperature values for the sensor on the specified date. Today, usually at latest, but must be configurable, ordered by timestamp. So latest first. Very well. And finally, a logical data model. Here, all what we did before, application workflow and conceptual data model, that was very general. So you maybe would like to use the same approach for every database you are working with. Now we already start Cassandra thinking. So logical data model already uses Chebotka diagram developed by our dear guest. By the way, that over last years working at developer relations for Apache Cassandra and DataStax Enterprise, I've shown those diagrams so many times, but that's the first time in my history I'm doing that together with their developer creator. So let's move on. Logical data model results from a conceptual data model, but organizing data in the Cassandra specific structures based on the data access patterns we just covered on the previous slide, identified by the application workflow. Logical data model can be captured and visualized in the Chebotka diagram you see right now. And it can feature tables, materialized views, indexes, and so on. Logical data model still is not the thing we are going to put into the Cassandra. We need to do one more step. It's maybe not enough, but we already start to think about the queries we are going to execute. So, diagram you see on the right looks very close to diagram you've seen on the previous slide, because they're very related to each other. We start to think of the networks table, not optimized yet, but still. We have networks. It's going to be a single row per partition table. We think to use name as the key. Maybe it could have been ID as well. We will need description, region, and number of sensors. Why we have number of sensors? There is a nice point to mention. Cassandra is a big data ready application. And in many cases, you are going to do just a select count all. It may be a pretty bad idea because you do have really a lot of data in this field, and number of sensors per network may be pretty big. So in our case, we want to cache this information about the amount of sensors. So we will be able to show information about the number of sensors per network, showing the network page or list of the networks we are working with, without doing any queries like select, count, all, blah, blah, blah. So in some networks, it may be a pretty heavy operation. Well then, what's the next important point for us? We can think of temperatures by network. Notice, we are going to have temperatures by sensor and temperatures by network. That's what called denormalization. So we are duplicating information, and it may be okay, in this case that's not exactly the duplication because we are storing average temperature, but in some case it may be a duplication as well. Duplication is not bad as long as you control that, but allows us to get the results immediately, avoiding any kind of additional queries on the runtime. So if anyone wants to open a page, the page should be opened very quickly. Results should be delivered immediately. We don't want our users to wait. Waiting is the worst. We want to deliver fast applications. So, when we speak about the temperatures per network, at first it will look like network, which is going to have the network as a partition key. It will also have clustering columns with date and hour, so they will be sorted as required at the previous state of the application workflow. Temperatures by network must be sorted. And we add sensor ID as a clustering column. It's not really required per se for the heat map, but that's required because, don't forget, primary key must ensure uniqueness. So network date and hour will be not enough for the primary key in this case. When we store data columns, those are going to be average temperature, pretty obvious, then latitude and longitude. And notice, average temperature is the aggregated column we prepare beforehand. And speaking of Q-free or query-free sensors by network, well, that's pretty obvious list of sensors per network, where network is going to be partition key. I expect a lot of sensors per network, but not, let's say, billions of them, and so it's still fine to have it like that. We have sensor as the clustering column. Why? Because first we want to, because we again has to ensure uniqueness of every row, and every network is going to have multiple sensors, of course. When we store latitude and longitude, so locations, and some characteristics, we don't tell how exactly we are going to store characteristics, because it's yet logical data model, so it's not the final one. And finally, temperatures per sensor by sensor are going to be pretty simple table. We have sensor as the as a partition key, sorry, and that's a composite partition key because we use also date. And date key is very important. That's one of the typical mistakes. You start to think of a partition size while developing a data model, and you think, okay, that's not going to be big, and you do sensor timestamp value. Will it work? Yes, it will, first few months. But then, as every sensor reports more and more values, partition will grow, and it will be too big after all. So here we are adding a partition key of date to have the bucketing and have multiple partitions per sensor for different values of different dates. Finally, we are going to store timestamp. Why? Again, first for sorting, and second to ensure uniqueness, or maybe opposite, first for uniqueness and second for sorting, because uniqueness is a very important thing. And finally, we have data column, which is going to be value. And now we are getting to the very deeps, and now we are getting to exactly that thing which will define create table statement we are going to do next. So that's the physical data model. Physical data model is directly derived from a logical data model by analyzing and optimizing for performance. The most common type of analysis is identifying potentially large partitions. Why? Because large partitions are your worst enemy if you want your application to be efficient. Simple as that. Some common optimization techniques include splitting and merging partitions, data indexing, data aggregation, and concurrent data access optimizations. So let's take a look on the things what changed. First of all, to avoid possible issues with the situation when we will have a lot of buckets, a lot of networks, sorry, be adding buckets into the networks. And this bucket is just a text value, which is going to be partition key. What kind of a bucketing you want to use, it very depends on the particular use case. For example, it may be a country. So we will have a group of networks by country. Or we may have them split using some geographical definitions. There are many options in general. Well, name. As we have bucket as a partition key, we need to ensure all the networks to be unique, and name will work as a clustering column, and we're still doing sorting based on the name, so it will be easy for customer to find proper network he or she is going to work with. Our fields in this case are the same: description, region, and number of sensors. Nothing changed beneath them, but those are data columns. And that's enough for the first table I'm going to work with. Speaking of Q2 and the second table, there is a couple of very nice optimizations I need to cover. So we discussed what we need partition key to be network. But that's not enough, because we are going to store averages for a pretty long time. So we will be able to walk through years and dozens of years, maybe in the future hundreds of years, step by step. And of course, then this partition in this table will grow too large. And we have to avoid that. Otherwise, operation teams will be very angry to you if you don't do optimizations like that. So in this case, we are doing bucketing again using week, and this week, which is a date, will be second part of our composite partition key. So we have network and week, and our temperature by networks table will be partitioned by network and week at the same time. Composite partition key. Two column values go into the partition, and as a result, we will have them grouped by week and network, so we can easily work with them and walk through week by week, month by month, and so on. Then one more thing, date hour. We group date and hour together into timestamp. It's going to be clustering column sorting order descending, so we will have them sorted by time. And finally, we have sensor, which is a clustering column, which we need to have just for the uniqueness of a record per date, hour, and sensor. That's it. Otherwise, so average temperature is going to be float, pretty obvious, and latitude, and longitude will be decimal. Speaking of Q3 and sensors by network, we have it looking mostly like it was before. And temperatures by sensor, again, is pretty predictable. We go with sensor and date, which is text and date accordingly are the partition keys, and timestamp as a clustering column. Artyom, are there any things you would like to add, maybe?
Yes, we got a lot of questions here. So I would like to answer. I don't think I will go through all of them, but maybe some of them that I remember and I think are very good questions. So one question is, we added these buckets for the networks table to merge partitions. So we didn't split partitions in this case, and yes, we did it for merging partitions. So essentially, if you look at the logical data model, then we had name of a network as a partition key, but our access pattern Q1 asks us to retrieve all the networks. So essentially, we're going to retrieve everything from that table, all the partitions, right? So we are going to create a multiple. Those partitions will reside on different nodes in Cassandra, and we don't want to touch different nodes. We only want to touch one partition. So we merging all those partitions into one single bucket, partition with partition key bucket, and the valuer can be any dummy value there. So something like all or default, and you only have one partition in that table, and all of your networks in that partition You can retrieve them efficiently, and this is the optimization. Instead of if you have 10 networks, in the logical data model, you would retrieve 10 partitions. In this data model, physical one, you retrieve one single partition. Now, another question for the temperatures by network, why do we have sensor there as a clustering key? So this table, for each network, it's gonna store average temperature for every sensor for every hour, right? So if we don't use sensor as part of the primary key, and then we are going to basically lose information because we need to store for each sensor. But it's also important where we put the sensor in the primary key. It cannot be partition key column, right? Because we are retrieving all temperatures by network. And then can it be first clustering column? Probably not. And not probably, but definitely not, because our access pattern asks us to also order the results by date and hour, right? So it's hourly temperature, hourly average temperature. So it has to be added at the end, right? So we don't destroy the ordering based on date, hour. So another question was about how about, so we combine their date and hour in temperatures by network. Why not combine date and timestamp in temperatures by sensor? So this one is easy because date is actually the partition key column and timestamp is clustering key column. Right? So we cannot combine that, because otherwise we will have, basically, if we just make timestamp as a partition key, then we will not be able to order based on timestamp. We will not be able to do range queries and so on. So another question, I think, related to networks and bucket. So I was under the impression that having all your data as part of a single partition was bad. So that's actually the opposite. Your partition should be organized so that it contains all the data that is needed to answer one single query. Now, the problem there you may have is if that's a lot of data, if it's hundreds, thousands of rows, and if it's hundreds of megabytes of data, then you want to split that partition. And this is what we actually did for the temperature by network table, where we introduced week as a new column, as a partition key column. So our partitions before, they grew just uncontrollably, infinitely, based on the time, right? The more data you add, the larger your partitions become. But now each week we'll start a new partition. Okay.
I would like to answer one more. If you've answered that already, please stop me, because I was reading questions. So in IoT use case data model, if my sensors are moving across network, if we need to list sensors of a given network, what should be the data model? Well, first of all, if sensor is moving across networks, so from one network to another, it basically means what these sensor is moving geographically. Like you have sensor, I don't know, in Houston, for example, and you are moving this sensor to, I don't know, Alaska. What's then? We have to think what it affects. First of all, it shouldn't directly affect temperatures by network table anyhow, and we don't have to do anything with the data, because, okay, now it's moved, but the fact we move it with sensor doesn't anyhow affect average temperatures in Houston, correct? So temperatures by network, from my point of view, should not be affected anyhow. We just keep writing data to this table with understanding what latitude and longitude for all the new records should be changed. That should be pretty clear. Well, it's going to go to another network if it's a cross-network moving. Then networks table, we only have to change number of sensors. -1 + 1 for the new network. Sensor by network, well, we are removing one sensor and adding the same to a new table based on the network we are working with. And for temperatures by sensor, I'm thinking as they don't store any kind of latitude and longitude values, that should that matter at this point? That's a good question. Maybe if you would like to move from my point of view, like let's say from maybe not scientific but very practical point of view, if you want to move network, maybe the easiest way would be to decommission sensor, so prevent it from running from the database, set it to the new network and enable it with a new ID. So for the database, it will look like a new sensor with completely new data. This way you will avoid any kind of collisions. That's what I would think first of, and maybe Artyom has another opinion.
Well, so it's the moving sensors question, right? Yeah, so one thing you can notice, we have the sensors by network, and we have latitudes and longitudes there, and that's where you can store the current location of the sensor. But each time you store a measurement, then you will have to duplicate latitude and longitude for that specific measurement. So this is so for example, temperatures by sensor, we will have to add longitude and latitude there and store everything for each measurement, what was the location at that time. And for the average temperatures, then you have to kind of decide on maybe store the region or something like that. But because you have like, if the sensor was maybe store the path of the movement of the sensor and things like that. And I think we may have even more questions.
But we have to go on.
Yeah, we have 2 more examples. So.
Yep. So yes, we have to go on. I'm sorry if you have your questions not answered yet. But again, we aren't dropping you out. That's what we are going to say to you. Use our Discord chat. I kindly ask our colleagues to copy-paste link to Discord chat so people will be able to join. And at second, we have the community.datastacks.com, which is kind of a dedicated Stack Overflow for all Cassandra-related questions. So, and we have to move on. With all the example, we are working right now. Now we have the table definitions. We have physical data model. How do we work with that? Using already Cassandra query language. Very simple. We have the sensor data modeling example, and we suggest you to pass it through after the workshop on your own. That's very important. It's not enough to watch. Please do your job. They are not so long. You are going to see it right now. And we start with the very beginning, and first thing we are going to need is to create key space sensor data. And as it's the demo application, I will use replication, only replication factor 1. I don't need any big replication here for the demo. And now I'm switching to sensor data key space using my use sensor data command. Now we are going to create the tables we just discussed. I will not stop on that for too long, but all those you've just seen already. It's the tables we discussed right now converted into Cassandra query language. Create table networks, bucket text, name text, description text, region text, number of sensors integer with primary key, bucket as a partition key, name as the name of the network and the clustering column. Now I will need temperatures by network. I'm also going to need sensors by network. And finally, temperatures by network. So I've just created 4 tables we have seen. That should be enough for us to go, and I can continue to the next step. Now, I will load a file sensor data SQL. So I will load some prepared data for this example. We don't want you to write it all from scratch. And the data is loaded. There are not so much, there are not billions. So we want these to be simple and readable for you. Now I'm going to read data from networks. So I'm executing select all from networks statement. And we already see we have 2 networks defined here. We have forest network, forest fire detection network, with 3 sensors inside, and region is going to be south. And we have VolcanoNet, which is a volcano monitoring network with only 2 sensors. As you see on north, we have not so many volcanoes. And they all belong to the same bucket. So that's important. I don't have to query. As long as I have only 2 networks, I don't really need any kind of a partition optimizations. So I use simple bucket all, and I read always from all, and I access one partition available with ease. I don't have to access many partitions, so it works very quickly. And finally, I do select network week date hour sensor average temperature from temperatures by network. And here I have my temperatures by network aggregations. So we have, that's in Fahrenheit. So don't be afraid. But here we have, like very different values. This one looks pretty solid. I guess this one belongs to... Yeah, this one is definitely look like an anomaly. But it works, so I get the data what I want to have. And then I can do select all from sensors by network. And I see all my... As I'm doing select all from sensors by network, those are all my 5 sensors. So everything what I want to see about them, we have 3 sensors in ForestNet, and we have 2 sensors in VolcanoNet. They have different IDs. They have different values, of course, in their metadata, let's say. So characteristics, that's a map of key value, and they may be different. You may want mostly probably to specify the model or the producer of your sensor and so on. As it's a map, you can store basically a lot of different key values there. And of course, latitude and longitude. Okay. And we can do finally, to review last one, select all from temperatures by sensor. And this table looks easier, so that's basically the main table for us. We have sensor, date, timestamp, and what was the particular value. Good. So, but what comes next? We have to design query for the use case 1. We need to find information about all networks, order by name. To store or to save a little bit of our time, because we have more examples to cover, I will just open up the solution. I hope you forbid me this little cheat. But I do suggest you to do it for you to do it on your own. But we simply need to select name, description, region, and number of sensors from networks where bucket equals all. That's the predefined bucket for the beginning of our way. If in the end our global monitoring system will have too many networks, we will start splitting them. But this approach is very convenient. So we have bucket. Bucket is predefined, it's easy to use, and at some point I'm going to have too many of them, too many of the networks. I will not have to... The point is, with data modeling, you cannot alter partition keys. Why? because on the big tables and big data loaded into the Cassandra, changing of a partition key will lead to changing of the partitions and reshuffling the partitions all over the cluster. And again, when you have petabytes of data, that's going to make your cluster pretty busy for some hours, maybe days, or even longer. So in this case, we do very nice optimization to avoid possible changes after some months or years of our work. And that's a really cool optimization. So I'm doing my Q1 statement and I have all what I need: name, description, region, and numbers of network. So that's something what we can start showing our customers or users already. Speaking about the query Q2, find hourly average temperatures for every sensor in network forest and range 5th of July 2020 and 6th of July 2020 within the week. Do you remember we are having these weeks or buckets based on weeks, and every Monday will be beginning of a partition for us. So we order by date and hour. And again, I stick to the solution. Thank you, Artyom, for the predefined solutions for us. It's just very on time. And that's going to be our query. We select the required data from temperatures by network. When network is the network we want to access, and week we are going to access, and date hour higher and lower than the specified. So luckily we have those clustering columns, and we may use inequalities. With a partition key, as Artyom said today, you cannot use inequalities with a partition key. Boom. And we see everything what we need. So we have these hourly averages to cover different situation in the network and how it changes over time. And we again can use some, I don't know, Grafana or any another visualization tool to show this data. So that's already works pretty good to us. And a couple of more solutions. We have to find hourly average temperatures for every sensor in network forest net and date range within the weeks, within 2 different weeks. Like when we have a situation when we have to query data from different partitions. We are having, don't forget, we are having these partitions by week to avoid too big partitions, which may be dangerous for your database efficiency. And first solution we think of, we can go with this approach. So we will have basically 2 queries. First query to query 1 partition, and second query to query 1 partition when you unite your data on the application layer and show the data to a customer. Of course, it's not convenient. So what we prefer to use here is a very nice thing called in. So we cannot use inequalities for partition keys, but we can and sometimes should use in. And here we go. We load all the required data from temperatures by network, the network, our forest network, and the week in array of the 1 week we need and 2nd week we need to have, and date hour is specified as usual. So we have things like that. They will give the same result. Oops, you bring me back. Yes, they will make the same result, but with a solution 1, you has to do more work in your application. So usually lazy developers are more efficient developers. So I don't know about you, but I would definitely stick to the second solution in this case. We are getting close to the end of the first example, IoT or sensor data example. And finally, we need to find information about all sensors in network forest network. So again, you can start typing select all blah 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 blah, but you can type, if you never use it, Katacoda is a great tool, you will love it. But again, I will push the solution button, and that's as simple as that. Select all from sensor network when network equals forest net. Boom, we are done. We have 3 sensors and we have their data. And our final solution for the query Q4, find row measurements for sensor ID on the given date, order by timestamp, and that's a very simple statement. So we are selecting timestamp value from temperatures by sensor ID and date, and that will be completely enough for us. Oops. Okay, I pushed the wrong button. Yeah. So now we have all we need here. And you see how it works. So I'm easily read the wall partition. It's not a big deal because all the rows in the partition are stored together. They are neighbors. So they're always easy to fetch. We store together what we retrieve together. Makes sense for me. And congratulations, we just completed this scenario, and I don't know about you, but I'm very impressed with this scenario, so I will definitely set the higher mark for that. And you know what? Enough of me. As long as we have Artyom here, let's ask him to do the next example, I think. So give me a moment to switch to your screen. Okay, so you are good to go.
Okay, so a few more questions. We got a few more questions, and I will try to address them. So by dynamization, what we actually mean, it doesn't mean you're gonna try to apply normal forms or try to understand what normal form your table is in, and you try to go to a higher normal form. It means basically two things: the duplication and data nesting. So things that will have to be avoided in relational data in normalization theory, like based on functional dependencies. So you duplicate data, and that's fine in Cassandra, and you nest data. By nesting, I mean those multi-row partitions. If this sensor data example, IoT example, all four tables, it's a simple example, the simplest one, but all four tables had multi-row partitions. So most of your tables, most majority will likely have the multi-row partitions. That's nesting. You nest in multiple rows into one partition, and you duplicate in, like, okay, the location of a sensor will be duplicated into different tables. And sometimes you have to also be careful about that and see how much duplication you are doing, right? So in particular, the problem could be that you may duplicate your data. Basically, it grows over the time. There is no limit. It's not like factor of 5, which may be fine, but you just have the linear the kind of function for that. So another question. How do I delete partitions? Maybe the data is expiring. We can discuss it on the next example. Also about averages. How do we compute averages? We can discuss on the next example. Secondary indexes on the diagram are denoted just by IDX. Again, the primary use case for secondary indexes, and we have just the regular ones, nowadays sometimes called legacy. We have SASE indexes, and we have newest, they are not part of Cassandra yet, but they are in Astra, SAE indexes. And they are all secondary indexes. They all represent the local indexing technique. Versus tables and materialized views, they are global indexing or distributed indexing. So the primary use case for secondary indexes in real-time applications is you query large partitions. If you in your query you specify partition key and then the index column. So searching within large partition. For analytical application where you retrieve a lot of data, you can use secondary indexes for many different things. But for real-time, this one specific. Materialized views are great. They give you convenience. Instead of duplicating data into a different table, organizing it differently, you just create a materialized view and it's maintained automatically. But there is a limitation. You can only add one column into the primary key of the materialized view. So it's not like you can do all kinds of changes. So for example, in one of the examples, I could have used materialized view. We didn't see that example, but I decided not to because I put the same data into like 4 or 5 tables. And for maybe one of them, I can use materialized view for convenience. but I still have to manage the other two myself. So why not to just manage 3 of them and just use one technique instead of the 2 techniques? Batches. For batches, so batches kind of seems to be logical to use them to maintain consistency of your duplicates, right? The copies of your data in different tables, different partitions. So again, the good use case or the suggested use for batches is to combine statements like inserts and updates that only update data within one partition. So these batches are basically called batches, single partition batches. Okay, so if you need to insert data into multiple tables, batches will not be a good efficient solution. So instead, you just use multiple inserts without batches. So multi-partition batches are not very efficient, so you should avoid them. And by the way, materialized view secondary integrated batches. Go to the datastacks.com/dev on the main page, find the Cassandra fundamentals course, and look at those 3 specific topics, which describes the limitations of each one and use cases of which one, much more detailed than what I provided for you. When to use in and maybe not to use in. So in is not a bad or good construct. It's just a construct there that allows us to creating multiple partitions, but sometimes we can use it with clustering columns as well. So it can be within partitions. So the only thing we said, we want to create as few partitions as possible. So when you use in, just make sure you're not adding there in for the partition key column. Just make sure you're not adding a lot of values there, so you're not retrieving data from many partitions. In our examples, we used in for multiple weeks. It's just because we had to. Basically, we introduced column week to create buckets, and now we had to retrieve data from 2 buckets because from 2 weeks, just because the query was like that. So it's not a bad thing at all. And another thing I will mention for the certification, those of you who will take the certification exam, the data modeling questions, all based on the sensor data example that Alex just covered, and another example which is messaging. It's a second example in the collection, but we're not going to talk about that one. So get yourself familiar with those examples. It will help you to recognize those diagrams and answer questions right away. Okay. So the second example we'll talk about is actually also very related to the first one, because it's a more generalized example of time series. What happened with sensor data is it's an IoT example, but essentially the most important part there was collecting those temperature measurements and storing them and then creating them. So those temperature measurements are essentially time series. So where we have the some kind of failures that are reported usually after specified and constant time, and those values are indexed based on time, and they represent time series. So time series is just a collection of measurements over time, and they can be represented by a function as well. And time series are not only used in sensor data. So for example, you may have some kind of wearable watch or some kind of other bracelet that will measure heart rate, or maybe will measure the temperature or something like that, or the number of steps you make and things like that. So those are also time series. Then you have in your house you have something simple like a thermostat, which measures the temperature inside of your house and adjust your AC system accordingly. So that's another example. And smart homes have more and more sensors that allow you to collect the data and analyze it and make decisions based on that. So this example of time series is essentially generalized example, and it does cover everything that we talked during the sensor data, but it's more generalized. It can be applied to actually different IoT domains. Okay, so again, a time series is a sequence of data, points taken at successive and usually equal spaces, spaced out points in time. So the data point is what used to be our temperature. Now it's just in general data point. And we had a sensor, but now it's just something we call source or subject. So we have this source that generates the data points. And we have that the data point is not specifically temperature, it can be something else. So data point is for a specific metric or variable. Right? So maybe it's humidity, or maybe it's the heart rate. Okay, and sources are usually organized into groups of sources. Like sensors belong to sensor networks. My Apple Watch belongs to me, right? I may have multiple variables that all report data about me, about a person, right? So person can be a group as well. Or maybe I have multiple thermostats, so I may have video cameras, whatever other sensors inside of my house, and the house becomes a group which contains all that information. The difference, of course, will be that there will be different characteristics. In a sensor network, you may have thousands of sensors. In a smart home, you will have maybe a dozen, maybe less, maybe a couple of dozen. So it all depends. Okay, and similarly, so different domains will have different constraints, and that will affect mostly physical data model. Okay. So again, I'm going to read. So this diagram, again, just to understand your domain, your data. It's not Cassandra specific. I have sources that generate data points for metrics. Each metric is described by name and has unit of measurement. Maybe Fahrenheit, maybe it's going to be the inches or any other unit of measure that we take. And then the data point is simply timestamp and value. Again, the timestamp is not enough to identify the data point. So in this case, you can see the data point unique identifier will consist of source ID, metric ID or metric name, and the timestamp itself. So there's three things that you have to see. And now sources can be organized into group. You can see one-to-many relationships. You have many-to-many relationships. Okay. So now the purpose of the application workflow is to understand how we're gonna use the data. How are we gonna use it in our application? So those data access pattern doesn't have to be only queries. They can be inserts and updates as well. In our case, they are mostly queries. So here we have 5 tasks. Show all data sources in a group. Okay, so we need to organize. If we go back, so we need to organize, right? For each group, we need to get all the sources. So we need to basically nest all the sources that belong to one group into single partition, right? Based on that query. Show all existing metrics. That will be simple, right? We have all the metrics in one place. There is no relationship there involved. Explore, and then we have explore time series by source, by metric, and based on statistics. And you can look at those queries. So there are two for each one. Let's look at this third and fourth first. So retrieve time series with a high resolution of 60 seconds for a known group, one or more, so multiple sources. So when you say a known group, I know I will use it as a partition key. When you say multiple sources, then I say, oh, I know that I don't want to create multiple partitions, so the multiple sources will be my clustering column. And then time range spanning at most 10 days from now. So time range means I'm going to have to query based on range, and that the time will have to become a clustering column. So this is how those queries help me to organize, to start thinking about how I organize the data from conceptual data model for my logical data model. Then there is ordering. So ordering by source, timestamp, and metric. Okay, because a sensor, the same watch can actually take multiple, produce multiple time series for different metrics. Okay, and then query 4, we have the retrieve time series for a low resolution of 60 minutes. So this resolution, what it means? It means that my sensor is going to record or report a value, generate a value every 60 minutes. That's a low resolution. The previous query, 60 seconds, that's a high resolution, and so on and so on. Right? It can be different. So you can basically observe 4 things here. We're dealing with querying by source or organizing by source, by metric and by statistics, but also there is resolution involved. Okay, so at this point, I'm not going to go through all of them, but maybe, Alex, if we have a question at some point, feel free to interrupt me.
I would like to proceed and answer questions after this wall scenario, if you don't mind.
Okay.
So we will better understand the timing.
Yeah. So sources by group. This is my first table here that will allow me to retrieve all sources for a known group. Again, I look at the query, I look at the conceptual data model to understand what is involved there. And what was involved? There was a group, there was a source, and source was part of that group. So there was actually 3 things, and I need to kind of keep data from those 3 things. 2 entity types, 1 relationship type. Okay. The source is clustering key here because it uniquely identifies a source within a group, within a partition. Okay, each source will be a different row within a partition. Now for metrics, I'm basically storing metric by name and organizing them by name. So each metric will be in separate partition, and that's not ideal. We will optimize that. And this is, again, generalized kind of case of the previous one. So that will be a similar optimization that you've seen before. Now we have for each query, we essentially created a different table. Sometimes we can combine, sometimes a table can answer more than 1 query, but not in our case. So to be able to retrieve our time series, okay, and time series is a sequence of values, and each value is identified by what? By source, timestamp, and metric. So all 3 of them will be part of the partition key. But we are retrieving all time series generated by all sources from the same group. So in this case, group becomes partition key, and then based on the query, we saw that there could be multiple sources. We need to order based on timestamp, and we also need to add. We also need to order by metric based on the query, but we need to add metric for uniqueness as well. Okay, and what you can notice, this second table for the low resolution is the same. Okay, we're just storing less data there. Every 60 minutes there will be value, while in the previous table every 60 seconds. So each resolution will result in different table field. Now the second, the fifth and sixth, they organize by metric. So in this case, you want to know all the sensors, all the sources that report temperature, how they report temperature in my house. I have multiple thermostats, so here we go, I get those multiple sequences. Okay, and the QE7, the last one where we retrieve, so let's read this one because it involves statistics. So we get daily mean, max, median, mean, and standard deviation values for a time series with a given source, metric, and date range spanning at most 1 year. So we have given source and metric, those become partition key, and range of dates became clustering column because that's the only way to support range queries here. Okay, so key observation: multiple resolutions will require multiple tables. There are actually 3 common approaches used for time series, represented here: organizing your data by source, organizing your data by metric, and storing aggregates. Okay, how do we compute those aggregates? And we had that question for the previous example. How do we compute that aggregates? Not in Cassandra. That has to be done by external framework tool, and in our case, it's usually Apache Spark, where we will extract some data from some raw data, and we'll do the aggregation, insert it into new table.
We will need to prepare a workshop regarding that, because Cassandra and Spark are the best friends, and we have to show how they work together.
Right. So those statistical computation, those aggregates are not, they are expensive. So you don't want to run that in your real-time application. It's possibly you will separate your workload and have one data center running Spark, and the other one running just Cassandra, and the second one running Cassandra and Spark. So the data will be replicated into both, and you can use Spark to compute aggregates without affecting the real-time data center where it only answers Spark queries.
Sorry, Artyom, I wanted to add one word regarding that. A lot of people asking me, like, okay, why cannot I have more aggregations in Cassandra? Or why don't I have like distributed transactions in Cassandra with commits and rollbacks? And that's still a very popular question people keep asking all the time. Answer is simple. Cassandra is designed to work with a very big data and still dispatch your responses within very tiny milliseconds. And if you really want to work with big data all over the world, getting your answers within milliseconds, there are indeed limitations implied. So that's the price to pay if you want to have your data that's like real-time database. You want it, you want to get it immediately. And the aggregations over billions of columns and over petabytes of data, over thousands of servers, of course, using the things like that, you cannot guarantee the response time, because it may take ages, it may take hours in some cases. So exactly as Artyom said, for some of cases, you may want to have Apache Spark alongside with Cassandra for the analytics workloads. But yes, so there are things like that to consider.
Yeah, that's right. And another question I got is about the table names, in particular the series by source. Should it be named series by group instead? So in general, when I name the tables, I use partition key like series by group or series by group and metric. But sometimes I basically, that's a common rule, but sometimes I do something different, because really what we care here is not necessarily group, but the source. And for the second series by metric, again, group is there, but we really care about metric there. And So group game is more like for, in addition to the main kind of framework where we deal with sources and metrics and organize our data by that. But yeah, you can also there is a limit of how much I can, how long name I can, my name can be on the diagram. But yeah, you can call it by group or group by end metric for the second type of tables and so on. Okay. So now in terms of optimizations, the first one, we simply merged all our metrics into a single partition because we are going to retrieve the list of them. And by doing that, again, we introduced bucket, and that's similar optimization to we've seen in the other example. Now, to decide whether we need to split partitions or not, we need to do some analysis. So, and that analysis will depend on specific constraints, specific assumptions. So for example, if you're gonna adapt this data model for sensor network, and in your sensor network, you can have hundreds of sensors. So means hundreds of sources in a group, then the optimizations will be different than if you're talking about a smart home where I have only 5 sensors. 5 sensors, maybe 3 metrics. So I'm reporting only 15 time series value every 60 seconds or every 60 minutes. So you basically analyze, and there are formulas to make the analysis more or less precise, but what I like to just analyze how many rows I have in a partition. So let's say I look at this table, series by source, high resolution. So what it means, and my assumption is that in each group, I will have only 5 sources, okay? And I will have, let's say, 3 metrics or some other number. But those have to be like worst case values. So in that case, in a partition represented by group, how many values can I have? How many rows? Right? Because each row will have a unique value. So we can say how many rows, how many values in this case. So you will basically have to multiply. I have 5 sources. Each one is gonna generate value every 60 seconds, right? So every minute, essentially. So that's 60 values. It's gonna generate, each source is gonna generate 60 values per hour, right? And then also each source may generate multiple metrics. So if it's 3 metrics max, then I also multiply that by 3. So this way I will take 5 multiplied by 60 multiplied by 3, and I will get the 900, something like 900 values, less than 1,000 values in 1 hour. But then you say, okay, what about 1 day? Because you will record the data. What about 1 day? Oh, it's now 20,000. What about 1 year? And now you okay, that's a large number, right? So you're now saying that you will need to your partition will grow to be too large. Okay, so you may need to split that partition. In this specific example, query 3 is actually only retrieves data for the most recent 10 days. So it's not gonna go to weeks, many weeks, months, or years. So after 10 days, you have to get rid of the old data. And the high resolution data, however, will be kept basically like for forever. Okay, so in case of the high resolution, in case of high resolution, all we needed to do based on our analysis, you can read it. It's in more detail if you want, but we only introduced source as a partition key, and again that was based on some math that you can read specifically, and maybe I can show you shortly. For the low resolution, because it keeps data forever, at some point we will exceed the desirable or the maximum desirable size of the partition. So introducing year there is a good way to split those partitions. Okay. And are there any questions that you may want me to answer?
I think we have to go on.
Okay.
So yes, and if you would make it full screen, it would be great.
Okay, so again, we start with by creating the key space. It's called time series. Oh, well, okay, we didn't start. In some cases, you may have an issue and you just need to restart. The CAD coder didn't copy all the needed data. Didn't have enough time, probably.
Okay, it looks like something is wrong with this scenario. Okay, that looks better.
Okay, we do have a limit on the number of concurrent users on CAD coder. That can be an issue sometimes when we have a workshop. So if many of you are running CAD coder right now, the same scenario, then that could be one problem. So we're creating key space here. We're doing this basically from the command line. And creating all the tables we just talked about. Okay, and again, if you look at these tables, all of them have multi-row. Okay, create all the tables. Okay, and then in this example, we have more data in CSV file, so it may take a little bit to load that data. I'm gonna just click all of them.
That's interesting to notice. What in this case we aren't using just CQLSH source command, but we are using dsBulk, a great tool for data migration and data loading, unloading to Cassandra, which was originally DataStax's proprietary tools dedicated for DataStax Enterprise, but it was open sourced this year or last year, I don't remember, not open sourced. I have to check, but now it also supports Apache Cassandra and you can use it for free. I have to check if it was open sourced finally, but now it definitely works with Apache Cassandra as well, and at least with my experience it's the best tool to load multiple data, a lot of data into Cassandra or unload, for example.
Yeah, and we loading over 600,000 rows here, and it's gonna complete soon, finish into different tables. But you can also notice that we load in, for example, this series low resolution .csv file. We're loading it into two different tables. Okay, one approach storing that data is series by source, another one series by metric. Okay, so we loaded all the data, and let's see again. So at this point, we can start CQLSH. Okay, and let's see how our queries look like. So find information about all data sources in a group, and this is like smart house application. So a specific house, right? They can be more groups, but for one specific house, we have 4 different sources, 2 thermostats, the freezer reports temperature or something else. We don't really have it listed here. And refrigerator reports something. And there can be more actually characteristics here. So if you simply remove the characteristics, so there is a map there. We only get in the model, but if we are not gonna get, if we get everything, we can get additional, but it's not super readable. So okay, so we get in partial view of our data in this example just for readability. For the second query, find information about all metrics. So they all stored in one bucket. So we get in the 3 different metrics and the units of measure for them. And then for the third query, we find time series with high resolution of 60 seconds for specific group, house A, source, refrigerator A1 and freezer A1, and time range specified here. So we also order by timestamp and metric. So this is how the query looks like. We specify group, source in, and we specify multiple sources in this case. So we retrieve 2 time series based on actually more than 2 time series. Okay, we retrieve time series from 2 sources. Okay, and because like refrigerator reports both humidity and temperature, we actually get in more than 2 time series. We're getting 3 time series in this case. You can see that how data is ordered here and can be easily visualized. Those 3 time series can be easily visualized using this data. It's ordered by timestamp. You can see it's every minute we get a different value. Okay, every minute we get a different value. In the case of query 4, we'll get pretty much the same type of result, but the values are different. The values are decimal values in this case because it's an average, 1 hour average essentially. And you can see the timestamps only have this 1 hour resolution. Okay, so it's a lower resolution. Okay, now retrieving based on metric. So everything in house A that reports temperature, let's see those values for a specific time range. And here we have the 4 different sources reporting temperature. Okay. And the lower resolution, again, will be very similar result, except the resolution by hour, not by minute. Okay, the last query is gonna give us the statistical information for a particular source and metric. So it's just one time series, one specific time series defined by source and metric. We have the daily averages, max, mean, median, and standard deviation. Again, these values are computed outside of Cassandra and simply stored there. Okay. Any questions? Because I don't think we will be able to cover another example.
Yes, I think we are out of time and we will go directly to quiz. But that's very fine. So let me take a look at the questions maybe. Okay, do we have those CQLs anywhere? Well, this one is easy to answer. Sure, we do. And you will get links very soon. So those exercises shown by Artyom and me They are open and publicly available, and you can go and do them all through all the steps. Good. So our time is almost over, and we are going to do just few last steps. So I will switch back to myself. Give me a moment. Okay, so it's now some fun time. We are running a quiz. If you have been at one of our last workshops, you know what to do. If you weren't, that's completely fine, don't worry. Because that's as simple as to go to menti.com and use code 566400 to join us. And we have few questions for you. The one who answers questions correctly and quickly, well, not actually we won, but we have prizes for the top first three places. We'll get some prizes, and that's amazing. So that's quiz time, always fun time at our channel. By the way, directly under Artyom, you have a subscribe button and like button. And if you didn't push them, but you are watching this workshop, that's the end of 2 hours workshop, so mostly probably you like our content. So when that's the perfect moment to press the like button and subscribe button. And I see more and more people are joining, and that's great. So we will be ready to go on in just a moment.
Alex, maybe you can show how to find those category scenarios.
Yeah, sure. So, okay, while we are waiting for a couple of persons, let me find you how to find these category scenarios. So, first of all, that's first place for us to be to put all the links and slides. If you want to have slides, will be GitHub, DataStax Devs, and we have these. That would be enough to start. DataStax Devs, Advanced Data Modeling Workshop Repository. And by the way, Docker learning path is not over yet if you are interested in Docker. But we go to Advanced Data Modeling Workshop. So far it has only slides. But what I'm going to do is to help you to find the hands-on part. And it will be hands-on exercises. Boom. Very well. So now we have all the required links right here, and you can go for slides or you can go for exercises from that place. In general, we have a lot of great content on Katacoda. So Cassandra data modeling, yes, for sure. But there are also many in other courses you may find interesting. So how to use Astra, so Cassandra as a service, managed Cassandra by DataStax. That's data migration learning and many others from the beginning and up to Kubernetes things, NoSQL bench, how to test your data model. So this workshop we speak how to design a good data model, but also there are ways to test your data model. Is it so good as you think about it? And that's we speak about NoSQL bench. Some things about Java, Spring, using storage attached indexes mentioned today, and many others. Okay, so I think we are ready to go on. And
how about the diagrams and the actual courses?
The diagrams are available. Okay, so that would be a thing to show again as well. You are right. So
datastacks.com.
datastacks.com learn
/dev.
data modeling by example. Thank you so much. And actually, I think I should add it to GitHub.
Let's go through datastacks.com/dev. And then there are a couple of things.
datastacks.com/dev. Oops, datastacks.com/dev. Sorry. And we have a lot here. So I don't know, whatever you would suggest to start with, Artyom, maybe.
So the things that we talked about today was if you scroll just a little bit up, and not just a little bit, scroll down.
Data
modeling. The learning series. No, down.
Sorry. More down? Learning series. Down, okay.
Yes. Learning
data
series,
modeling by example. Absolutely.
So the Cassandra fundamentals is you had questions about secondary indexes, generalized views, and batches. That's where you can find the answers, more detailed answers. But also, if you click on the data modeling by example and select one of those examples.
I'm going. Yep. And there are actually 5 examples.
Yep. And the first two will be, if you're going to take the certification exam, the first two will be on the certification exam. So you can click one of those examples and should see all the diagrams and actually the Katacoda scenario embedded into that page.
Yeah, so even don't have to go to Katacoda, but you can use Katacoda directly. And we discuss all the things with conceptual data model, an application workflow, and logical data model, and up to physical data model. And in the end, you have a skill building part with Katacoda embedded. So you can run Katacoda right here at the datastacks.com/dev or direct link, learn data modeling by exam. And yes, and that's amazing. That's a very new thing.
Yeah. Yeah, the question in terms of drawing the diagrams, I use the app.diagrams.net open source web-based tool to draw those diagrams. And if you need a template for doing an example diagram, you can email me. I can give you an example. You can reuse all those shapes.
Okay, so we have to proceed with Menti, and I see almost 100 of people has joined the Menti already. So we are going to have pretty nice competition here and few questions, very few questions, so we can start with. That's the quiz time. So warm up your hands, you has to be quick, but that's important still to give correct answers. Oops. Okay. So, first question. Answer fast to get more points. What's the partition key? An optional column to allow group by, a column to define partitions required, a required column to guarantee row uniqueness, the key to all the doors. Okay, and of course most of you answered correctly. Partition key is a column to define partitions required. It's not an optional, definitely. And partition key is a part of a primary key you need to guarantee row uniqueness, but only a part. So let me take a look at the leaderboard. I'm very curious who was the fastest one today. And it looks like it's Frosty with 925 points. Then very close, Jappreet and Nikolaus are making our top 3. But it was only first question, so let's take a look how it will go after a few more. And we start with the second one. Table can have many rows per partition. True, false, it requires special configuration in Cassandra YAML file. It's illegal. Time is very short. And it's over. Correct answer is yes, table can have many rows per partition. That's perfectly true. But notice you don't want to have too many rows per partition. That would be wrong and very bad for your data model. So, leaderboard. Intruder somewhere on top now. The 1,882 points, and Jappreet is on the second place with, well, some minor difference. And Smith goes to the third place. I see some familiar names. That's always fun to see some people attending our workshops not the first time. That's amazing. And Ahil was fastest. It was enough to reach the 5th place. Okay, question 3. Answer fast to get more points. I want to see how it goes. Inequality predicates are allowed on all table columns, partition key columns, clustering key columns. No inequality predicates are allowed. And time is over. So show me how it goes. Okay. And it looks like, you know what, Artyom, we has to run this workshop again one time, because 22 answered what inequality predicates are allowed on partition key columns, which is wrong. Only for clustering key columns you may use inequalities, and with partitions they are not allowed. And no inequality predicates are allowed, that's also wrong. You can use them with clustering keys. So, what are the changes? Who made a mistake? Let me see. So, leaders are here, and there will be some changes now. Ahil gets to the 4th place, fastest again, and Intruder, Jappreet keeping the 1st and the 2nd place, and I see Chan who got the 3rd place. Okay, so we are getting closer and closer to the end, and that's the question 4, and you have to answer fast. In the data modeling framework, we start modeling with physical data model, with logical data model, with conceptual data model and application workflow, with copy-paste from Stack Overflow. Let me see your answers. Time is up. And the correct answer is with conceptual data model and application workflow. Logical data model is the intermediate step in the middle. And finally, physical data model is the one we want to have in the end. And no one answered. We start with copy-paste from Stack Overflow. Come on, like, don't tell me you don't do that. I know you do. So, leaderboard. Were there any mistakes? And no, all the leaders answered correctly. But there will be some changes, I guess. So, we have Jappreet get to the 1st place and Chan to the 2nd and Charles on 3rd. Ahil has lost a little bit, getting to the 4th place, and Sam M is very, very close to them. So, we have one last question left, and that's the question number 5. Primary key defines row uniqueness. False. Correct. Primary key is deprecated. And time is up. And most of you answered correctly. Primary key indeed defines row uniqueness. Using together partition key and clustering columns, primary key ensures uniqueness of the row, so you can find the information you loaded into the database. So, how it goes on top? Who was quick enough? And okay, that's a real tight competition this time, but no big changes on top. Jappreet, Chan, and Charles who got to the top 3 in the end of the competition, but managed to do that. Congratulations to all the winners, Jappreet, Chan, and Charles. Please contact Jack Fryer at jack.fryer@datastacks.com, or please use our Discord server, which could be maybe easier. And claim your swag. For the best thing, just make a screenshot of your winning leaderboard directly on your mobile phone, and you will be good. Well, then we have 3 more questions. 2 questions from me and 1 question from Artyom. Before we proceed to what's next part, we have to ask you about something. First one, how do you like this workshop? On the scale from 0 to 10, I want to see your answer, how it goes, how useful it was for you. And it looks like we did a pretty good job. I have to notice what all the Cassandra thing is hard, and that's a very huge ecosystem, not just the database, but all the tools, friends, frameworks, and many others together, so we cannot answer all the questions within one workshop. But, well, then we have a special question regarding exactly this thing. So what do you want to see the most? Which code samples you want to see the most? That's going to be next one. So we got a lot of answers, and thank you so much for your warm answer and for your warm estimation. We are always happy to see numbers like that. What domain-specific data modeling example would you like to see in the future? And this question relates exactly to the data code samples and examples of the data modeling you did today with Artyom and me, and developed by Artyom and, well, many others in the developer relations team. I see finance, telecom, banking, gaming, messaging, banking and finance. Okay, Artyom, whisper us, for a second, what do you want to do next? Which kind of the thing you would like to show?
Well, for the finance and banking, I guess they could be related, and that's definitely something I will consider. Time series, I see would be interested to know what specifically else you want to see for time series, logistics. Yeah, I will consider all of them, and I will try to come up with more examples. E-commerce would be the next example.
Great. So you see, e-commerce is next.
In the works.
You want it, you get it. I see request for secondary indexes and I do understand. As secondary indexes is a special story in Cassandra, I would also love to have more materials regarding secondary indexes. Good. Log analysis. That's interesting. I want to take some existing SQL database and move it to Cassandra. I do understand Cassandra offers a lot of great benefits, but that's not always easy to migrate. Fraud detection. I'm interested what is the read world example. And if it was supposed to be real world example, the things we are showing today and you can find in those samples are absolutely real world examples. A lot of companies using all the time. The ACID is a must. Well, ACID is a great thing, but ACID also is a lie. You cannot have ACID in the distributed environment if you want to have guaranteed response time. ACID is great, but it may become unpredictably slow under, for example, bad network conditions. So, sorry, ladies and gentlemen, ACID in the distributed databases will never be a quick thing, especially if you have a lot of data and a lot of servers. Cassandra as log storage for disaster. So, that people are keeping writing all the time. You see this scrolling up. We are adding more options. Medical healthcare, finance, banking. Okay, so let's move on to the next and last question, actually. If you didn't have time today to add something to this list, well, please write us on Discord or something. We cannot fulfill all of those requests, but the most interesting, of course, we will do. And finally, now not about the code samples, but about workshops. these workshops and upcoming workshops, what you would like to have there. Are there any feedbacks, suggestions, what you would change, and so on and so forth. So very last minute, I would say. More of these workshops. Oh, I really like this one, but you know, we have now 2-3 workshops per week at least. So I'm not sure if we can do more because, well, you know what, we have kind of a limited team. All the great people, but not so many of us. So we will try to do more. More quizzes. Yeah, quizzes are always fun, I know. We will try to do more. Development workshop series. We will do it again. We will rework old development workshop series and we will do it again. Best course in a long time I've been to. Structure it, well thought out and articulate. Thanks a ton. Hey! Thank you so much. Yes. Okay, so I think we are done for today. That's incredible to have all of you today and you did so great. So, last 2 words. Workshop assignment. That's never enough just to watch, but go and do it yourself. As you've seen, we have 5 samples and there will be more. And we have much more content on /dev, datastacks.com/dev page, and datastacks.com learn data modeling by example, and Katacoda, and finally the academy.datastacks.com. Second, ask your questions. You are not alone in this world. You can always go and ask us questions regarding these topics. For the bigger questions, we have the community.datastacks.com. It's like Cassandra specific data stacks Stack Overflow, let's say, and Discord chat for more of the conversations, less or maybe not Cassandra specific topics, and so on. They all are free and available in your browser, of course. And finally, you did a great job learning Cassandra data model today. Don't let it all disappear. Get your free voucher, pass the course at the academy.datastacks.com. It's free. And pass the exam. Usually it costs something like around $150 now. Maybe I'm wrong about the exact price, but with a voucher you are getting right now, it's free. All completely, and you are becoming a Cassandra certified developer or administrator absolutely for free, and that's a great boost to your career. That's an incredible thing. So what are the conditions for those vouchers? As far as I know, there are no particular conditions, but you have first to be registered for this workshop in the Eventbrite. You have to go to bit.ly/get-voucher. You have to register using the email you are used for this workshop registration on Eventbrite, and this form is going to be closed pretty soon. So, be quick. Pretty soon, I mean pretty soon tomorrow. So not like in the next 2 seconds. Don't run there. You still can say goodbye to us. And finally, it was Artem Chebotka and Aleksandr Volochnev, developers from DataStacks, and we are very happy to see you here. Thank you for being with us. You are amazing, and thank you for all the questions. If we haven't answered your question, you know where to go. community.datastacks.com or at our Discord server. Artem, thank you so much. Спасибо.
Thank you, everyone. It was my pleasure.
Sure. Okay, so see you next week. And if you have some friends you would suggest to watch this workshop, we do it one more time tomorrow. And I will ask Jack. I don't know. For me, it's going to be... You can find it on Eventbrite anyway. You all registered for this one. You will have a link in the description of the video. Okay, so thank you. And see you next week, or maybe even this one. Ciao!